So this is an explanation for the answer key. Question number 1. This question is asking you to draw a force diagram, and as you would notice that there is no forces going this way, while the ball is indeed traveling this way. A lot of people made the mistake and put applied force because they assume that if the ball is traveling this way, then there must be a force pushing it in that direction. However, if you look at the question carefully, it says, draw me the force diagram after the ball has left the person's palm. Now, in physics, there is a very important concept, which is if an object is traveling in a certain motion, unless you have unbalanced forces acting on it or a new force acting on it, otherwise, the object will keep traveling the same direction that it was traveling. So for example, in space, if I threw an object in this particular direction, it will start to travel at the speed, and even after my palm has left the object and no more forces are acting on the object will still travel in the same motion that it was traveling because there are no new forces acting on it. So this object is going to continue traveling in that direction at the same speed until the very end of the world. Now, same idea. On Earth, even if I have gravity and other forces like that, even if I throw an object this way, the object will continue to travel. However, the motion might be slightly different because now we have also friction and air resistance acting in place. But the idea is that the object will still travel that way because I've had a lot of applied force applied to it before it left my palm. So the ball will continue traveling this way with a little bit of friction and air resistance dragging it that way. And so, yes, it will continue to travel in this direction, but the velocity will become slower and slower and slower. Eventually, it will come to a stop if it doesn't hit anything. Now, let's look at the horizontal forces. There are vertical forces. There are two vertical forces, normal and gravitational. I'm going to trust that you guys know what the definitions are by now. But you have to draw these two arrows in exactly the same size. Because if the gravitational arrow is much larger than the normal one, the ball will actually punch through the ground and go into the center of the earth. Oppositely, if the normal force is way bigger than the gravitational force, then the ball will start lifting into the air, and it'll be magic, not science. So I think we have already explained why the ball is going at a deceleration motion towards this particular side. Question 2. This is a distance time graph. And yes, Ethan's running a 100 meters race using minutes as a unit of measurement, which means he's super slow. A is acceleration, and you can see that the change in the distance is getting greater and greater, so it becomes a slope like that over time. And then this one is deceleration because it was covering more distance at the beginning, but then as time goes by, it's covering less distance. And this right here is a constant speed. It means that the distance being covered per unit of time is maintained consistent throughout this journey. And this again is acceleration, deceleration, and then this, as you can see, distance did not change. It was a flat line. But time is still passing. So that means that person stayed at the same spot for these 3 seconds. So that means the motion is stationary. So his time for finishing 100 meters is 11 minutes. Now this graph down below is slightly different. This time we're not talking about distance versus time. We're talking about speed or velocity over time. And so the way you would interpret the graph would be slightly different based on these lines. A is acceleration because although it looks like a straight line, but what it's telling you is that the velocity or the speed is increasing as my time passes. So a change of velocity is acceleration. This one doesn't mean that the person is not moving. It means that the person stayed at this particular speed for the next 4 seconds. Sorry, 4 minutes. And then this one, as you can see, the speed of the person was dropping until it dropped to absolute zero. So this is deceleration. And then this is stationary because the speed is zero, meaning that the person is not moving at all. So this is stationary. Calculate acceleration for phase D. So acceleration is calculated by this formula, which you have been provided with. This triangle thingy, this right here, means change. All right, it's just a symbol we use for change. So this means the change of velocity divided by the change in time. So the amount of increase or decrease in the velocity over how much time was used to have those changes. So as you can see, the change of velocity in this case, if we're looking at phase D, is 0. Velocity hasn't changed at all. It stayed at 0 the whole way through. Change in time was 13 seconds minus 10 seconds. So in total, 3 seconds were used. And then so 0 divided by 3, you're going to have 0 as an answer. Question 4. This diagram is looking at a block that is initially traveling at this direction. So this symbol V is velocity. It just means that, okay, the block is traveling in this direction with a certain speed, but they're just not providing you with exactly what speed. And then here you can see that there are 2 balanced forces, which are 10 newtons each. And these are horizontal forces. So given this diagram, do you know what type of motion the block is doing? And the answer is C. It is moving to the right, because that's what the velocity is, towards the right, with a constant speed. The reason why it's a constant speed is because it is moving, and the 2 horizontal forces acting on the object is exactly the same. So that means they're balanced. When you have balanced forces, the type of motion is not going to change. And also, it's not going to do any increasing or decreasing in the velocity. It will keep the current velocity it has. So you could either only have constant speed or stationary as a motion if you have balanced forces. If it was acceleration to the right hand side, what you'll see is a much larger arrow and a much smaller arrow this side. So the block will start to accelerate in this direction. But since the arrows are balanced, it is not acceleration or deceleration because velocity wouldn't be changing. All right, momentum questions. So question 5, momentum is calculated using this formula, P equals to m times v. So we are trying to find the car's momentum. So we need the mass of the car and we need the speed of the car. Mass of the car has been provided to you in the question. The speed of the car, however, or the velocity of the car, yes, it's provided, but it is not in it's not in meters per second, which is the universal unit for momentum. So we kind of need to convert it. So it was 50 km. 1 km has 1,000 meters, so that's 50,000 meters. And then per hour, so there are 3,600 seconds in an hour. So 50,000 meters divided by 3,600 seconds, it's going to give you 13.89 meters per second. And that is your velocity. So we sub in these values and we get this as a final figure. Question 6. This is a very challenging question that brings in the force of gravity and acceleration. So a 3 kg ball is being dropped and it took the ball 0.2 seconds to hit the ground. What is the momentum of the ball right before it hits the ground? If you wanted to know momentum, you have to know the mass of the object and the velocity of the object right before it hits the ground. The mass has already been provided to you. We just don't know what the velocity is. However, you can calculate it by using force of gravity and the amount of time it has been dropping. So if we look at gravity, you would notice that it's 9.807 meters per second square. Now, this one, meters per second square, it just means that it's meters divided by seconds divided by second. So you're dividing it by second twice, and therefore we have the square thingy. And this, if you look at the equation, it is actually also the unit for acceleration, because acceleration is velocity divided by time. So you can see that the unit for velocity is right here. Now this number means that for every second I allow an object to drop, that object will increase its velocity by 9.807 meters per second. So if an object is stationary and I start dropping it, after 1 second, the velocity will be 9.807. If I allow it to drop for another second, you just double it. So 9.807 times 2 is going to be 19.614. All right, so that is if you allow it to drop for 2 seconds. Now, we're not going to let it drop for 2 seconds. Instead, we only let it drop for 0.2 seconds. So we're going to do the same thing. 9.807 times 0.2 seconds, because that's how long you allowed it to drop for. And you're going to have your unit of measurement right here. And this, you would know that it is actually velocity. This is because 9.807 meters per second times a second, you're going to cross out this one with this one. So you're left with meters per second. And that is the unit for velocity. So that means by the time your ball is about to hit the ground, after 0.2 seconds of being dropped, it will now have a velocity of 1.9614. Sorry, 19614. All right, anyways, so now we can sub in the numbers. We have the mass, we have the velocity we just calculated, and so times it together, you will have this as your final answer. Part 3, collision. So for collision, if we look at this question, you would notice it is an inelastic collision scenario because you have a mass hitting another mass and then both of them move together with a single velocity in the same direction. So we're going to use this equation, which is the inelastic equation. We're going to first determine the mass of our object 1 and then the velocity of our object 1. This is the mass of our object 2, and velocity of object 2 was stationary, so that's why v2 is 0. And then what we're trying to find is the final velocity. So you just sub in all the numbers because you've been provided with everything except for this value. You sub in, do the math, and this should be your final answer. Next question. Okay, this time, again, we're going to look at an inelastic collision scenario because you have a cart that is moving. It collides onto another cart, stuck to it, and then move in the same direction together. And so again, you're going to identify your mass 1, mass 2, velocity of object 1, velocity of object 2, which is at rest, and that is 0. And then after the collision, you already have mass 1 and mass 2. You just needed to know the velocity after. And so again, sub in all the values and you should have this. Explain what type of collision this is. Well, it's inelastic because momentum is conserved, but kinetic energy is being lost. As you could see, at the beginning, before anything happens, your kinetic energy is much higher. You have this certain velocity, and then after the collision, your velocity has decreased. And velocity reflects how much kinetic energy a system has. Question 9. Well, this time, we are looking at the magnitude of the total momentum after the collision. If you read the question carefully, you have been provided all the information you need to determine the total momentum before the collision. And if you remember the concept of conservation of momentum, you know that total momentum before the event and after the event will be identical in a closed system and in a perfect collision. And so we could use this formula to help us and say, okay, total momentum after the collision would be the same as before, so we have to calculate the before momentum. And the total momentum before would be the momentum of object 1 plus the momentum of object 2. And how could you determine the momentum of object 1 and 2? Is by looking at the equation momentum equals mass times acceleration. And so we can expand this equation into this. And we can just sub in all the values we see. So M1 right here, M2, V1 is right here, M2, V2, just subbing it in. And now we can calculate this total momentum before the collision. And then this will also be the total momentum after the collision because of conservation of momentum. All right, next question. This time you have a bag of rice being tossed onto a trolley, and then together the trolley and the rice is going to roll that way. And so this tells you that it's inelastic because the two objects are moving together as a unit after the collision. So this is going to be the equation that we're using. We have all the information, mass 1, V1, mass 2, V2. V2 is stationary. The cart was stationary, so the velocity is 0 meters per second. And we sub all of these in, and we have M1, V1. Just plug in the numbers, and if you do your calculations correctly, this should be your final answer. Question 11. This time we have to interpret some graph. Now, if the question says that it is accelerating uniformly, you can ignore all these added bits. So it just means that tell me which graph represent acceleration, constant one. So this one is distance over time. The distance is not changing, but the time is passing. So that means the object has been stationary, not moving at all. This one, the distance increased consistently at the beginning, and then it stopped. And so that means the object has been traveling for a little bit of time, and then it became stationary. This one is a consistent increase in distance. So that means the object has been traveling at a constant speed that hasn't changed. Whereas this one has a slope. So that means it's increasing the velocity as the object is traveling. So remember, this is the distance versus time graph. Okay, next question. Now I'm drawing out the diagram because we have two objects, and so this is what it looks like before collision. You don't know what the mass of the second ball is. This is what you're trying to find. And after the collision, this is the traveling, okay? In this case, you can see that all the objects are traveling in the same direction. And so therefore, we don't have to determine whether the velocity is positive or negative because everything is traveling in the same direction. So I'm going to use the elastic collision equation, and I'm just going to plug in all the numbers. And if you do the calculations correctly, you should have the answer 10 kg. Question 13. So in this case, again, this is a elastic collision. And so we're going to use this equation right here. All the information has been provided to you except for the velocity of object 2 after the collision. And so I'm just going to plug in all the values as I see it and calculate this. And so this should be your final answer. Okay, question 14. This is more of a challenge question. I've provided you with this equation in the equation list. However, we haven't really formally taught it during the lesson. But this is a rather simple equation. Which graph best represents the relationship between kinetic energy and the velocity of the object? And this would be the one. Because if you look at this, velocity has been increasing. It's impossible that your kinetic energy stay the same. This one, velocity is increasing. However, kinetic energy is also increasing, so it kind of does make sense. However, you notice that if you do the math, kinetic energy and velocity doesn't increase one by one. So let's say, for example, if my velocity is 2, my kinetic energy would be 2. Let me see. 4. Yep. Assuming that mass is just 1. All right. We're using 1 as a constant for mass. And if velocity is 4, then this is going to be 8. So you can see how it is being doubled or quadrupled relationship. So it doesn't increase one by one nicely. So it doesn't increase in a straight line like that. Rather, if you increase the velocity by a little bit, the kinetic energy will be increased by a bit more. Instead of just doubling, it's quadrupled. I will show you that in a bit more detail later in the question. Okay, question 15 says that the car travels 40 meters due east, and the second car traveled this way. And during the periods of the travel, the cars definitely had the same watt. If you do the math, what you're going to find is that you could see the car traveled 40 meters due east. So if you do the momentum, P equals to M times V, you'd find that the momentum is actually 8. All right. Am I right? I can't remember exactly what I did during the math, but I remember calculating both of these to be 8. So, yeah, the average speed is the same, definitely. However, the displacement and the velocity is not the same, because if you think about this, oh, I remember. I did 40 meters divided by 5 seconds, so you have 8 meters per second. And then this one is 64 meters, and then in 8 seconds. And then if you do the math, that's also 8 meters per second. And so the speed is the same. However, one car is traveling west and one car is traveling east. So that means they're actually going at opposite directions. Now, the speed component doesn't have direction. It only has magnitude, all right? Whereas these are what we call vectors. So velocity, other than just the speed, also needs to tell me direction. And because they are opposite directions, so they have the same speed but not the same velocity. Displacement is also one. So displacement has the direction component to it as well. If you don't have the direction, we call it distance, all right? Momentum, again, it is a vector, so they have both magnitude and direction. And so all three of these are vectors with the component of direction, and so they wouldn't be the same. Question 16. So constant unbalanced forces means that you have acceleration, a constant one, being applied to an object for a period of time. Which graph will best represent that acceleration? Well, this is acceleration, this is time, but because it's unbalanced forces, and it says that it's a constant one, so the acceleration wouldn't be increasing, because for that acceleration to accelerate faster, the rate of acceleration to increase, the forces would be inconsistent unbalanced forces. So that means you're not going to increase that unbalanced force. This one definitely not true. This one, not true as well. This one is a constant unbalanced force. All right. Now, I don't think we will test you on acceleration versus time graph just because we didn't teach you in class, but I think it's a good concept to have. Sorry, I had to pause because I've been talking for a while and I'm getting a little tired. It's late at night. I sleep early. Okay, question 17. A lap cart is loaded with different masses and it's moving at a certain velocity. Which diagram shows the mass system with the greatest momentum? And you know that the formula for calculating momentum is this. And so all you have to do is just do your calculation. And then out of all three of them, you could see that this one has the largest momentum. And so that would be the answer. Question 18. Which paragraph represent the same type of motion of an object? Now, it would be this one, because if you look at this graph, it's displacement over time, so it's kind of like distance over time. This one shows that the distance has been increasing over time like that, so that means this is an acceleration motion. This one, velocity has been increasing, and you know that if velocity increase, that also means acceleration. Whereas these ones, if you look at this, displacement has been decreasing. So an object has been moving at constant speed back towards its starting point. Whereas this one, velocity started negatively. So that means I have been moving in a certain direction, but then I'm doing it slower and slower until I'm gonna start moving at an opposite direction, which means I am actually kind of, if I could show you with a pen, I'm moving in that direction, but I'm doing it slower and slower until I reach 0, and then I just started moving in the opposite direction and speed it up as I go. That's the type of motion that was happening. Let me erase that. And then for this graph, again, it's distance versus time. So distance means this is my starting point, and I start right here. I'm getting closer to my starting point, and then I go beyond it like that. Whereas velocity, this one is negative velocity, which means this is my starting point, and I'm going at a constant speed in this direction. So that is not the motion that we see on this graph. Whereas this one, displacement is a little weird because this is my starting point. The object is actually traveling away from the starting point, and then after reaching a certain distance, it turned back and head back that way. Whereas this one, it's a velocity over time. It means that this is my starting point and my object has just been traveling like that the whole way through at a constant speed or velocity. So that's not what we see. Question 19. Which diagram or diagrams shows a cart with negative velocity? Negative velocity would mean that the cart is moving in that direction. And if you look, this one has imbalanced forces, so the cart should be moving in that direction. And this one has imbalanced forces. This one's the larger one, so that's why I chose this one to be moving in a negative velocity. Whereas this one, the second question asks diagrams that shows the cart at equilibrium. So the word equilibrium, it means that my horizontal forces are balanced. And so you could see that the size of these are the same. The size of these are the same. And the vertical forces are also balanced. Sorry, horizontal is this way. Yeah, anyways, you could see that horizontal, vertical forces, they're both balanced for both of these diagrams. So that's why these two are in equilibrium. Question 20. In the diagram below, you have this, and I've drawn out the mass and the velocity for you. So all you have to do is just sub it in. You know that in the question it says the bullet has been stuck inside the block and they move together after the collision. So you know that you have to use the inelastic collision. So I just plugged it in, and this is the result I got. Question 21. It is a conceptual question. So a speedometer does not measure a car's velocity. It only measures the speed because velocity is a what? Well, there are two types of quantity in physics. One of them, we call them a scalar quantity, which means that quantity only measures magnitude. For example, speed and distance is a scalar quantity. It only tells you the magnitude. Whereas vector quantities has both magnitude and direction. So I've shown you a few examples right here, and I've color-coded it. Hopefully you can see them unless you're colorblind. So therefore this is the answer. Vector quantity has a direction associated with it. It is a vector quantity. Question 22. My cat is yelling and meowing outside my door. I shouldn't let him in. Now it's scratching my door. Okay, come in. Sorry, just trying to open my door. A cart has a mass of 2 kilograms and a speed of 3 meters per second, whereas this one has 3 kilograms of mass and speed of 2 meters per second. Compare the inertia and magnitude of these two. So inertia is something that we haven't quite taught in class, but you might have heard it in the video that we played you. So inertia is the tendency of an object that is in motion to stay in motion, or it's tendency of an object that is at rest to remain at rest. Basically, it's saying how likely it is for an object to change its current motion. It is a passive property, so it's a pretty vague idea in physics. However, if you think about it, the more mass an object has, the harder it is to change its motion. And so usually would say that an object that has more mass has more inertia. Now, if you do the math, P equals M times V, right? So the momentum of these two objects are actually identical after doing the math. They're both 6 kilograms times meter per second. However, the amount of inertia is not the same because one has a larger mass than the other. One is 3 kilograms and the other is 2. And so this is the correct answer. It has the same magnitude of momentum. However, the inertia is not the same. And the reason why we say same magnitude of momentum is because this question doesn't actually tell you the direction. So we can only address the magnitude of the momentum. Question 23. Which diagram represent a box in equilibrium? We've talked about this before. Equilibrium means that vertical forces are balanced and horizontal forces are balanced. In all 4 diagrams, this is the only one that meets this criteria. Question 24. You've seen this question before, however, this time we're asking for a more conceptual question. We're asking you to represent the velocity of these two masses using an equation. And so if you look at this, you know that we have to use inelastic equation. And so this is the inelastic equation. This is mass of object A. This is mass of object B, right here. This is the initial velocity of mass 1. And this is the initial velocity of mass 2. And because it wasn't moving, it's stationary, so it's 0. And so if you want to simplify this side of the equation, mass times 0, it has to be 0, so there's nothing. You can just cross out this entire thing and you're left with this. So we just write it here. On the right hand side of the equation, you have mass 1 times plus mass 2 equals the velocity. So we're going to just remain having this. And then after this, we want to take out, because we want to isolate this and say, what does V after collision equals 2? So we kind of have to find a way to transfer this onto the other side. And so you could do this, divide it by this. So you can cancel these two out just like that. And then do the same thing on the left hand side. And this is your answer. There you go. Okay, question 25. If the speed of a moving object is doubled, the kinetic energy of the object is what? Is it halved, doubled, unchanged, or quadrupled? Now, this equation has been provided to you in the diagram at the very beginning. So if we sub in some numbers and see how that changes kinetic energy, then we have these numbers right here. So what I'm doing right here is I'm making M 2. So I'm going to make M remain constant. So M is going to be 2 every single time. And then what I would do is I would double this V and see how KE is responding. So the first number I subbed in for V is 2. So if M is 2 and V is also 2, then after doing the math, I found that kinetic energy equals 4. This time, I'm going to keep M the same as 2, and then I'm going to double what I just did. So instead of having 2, I'm now going to sub in a 4, like this. Then I found that the kinetic energy is actually equal to 16. And then I doubled this number once again and say, instead of using 4, I'm going to have 8. For velocity and maintain M as just 2, just like before. And then kinetic energy becomes 64. And so you can see if I double velocity, I have actually quadrupled my kinetic energy. If I do a different set of number and say, okay, I'm doubling my velocity like this time, and then my kinetic energy is also still quadrupled. And if you sub in all the numbers, it would still show the same pattern. So as you double the speed of a moving object, which is velocity, then kinetic energy of the object will quadruple. Question 26. There isn't actually any information about velocity, so I'm going to ignore this question because I don't have enough information calculating momentum for collision. So ignore that. These are a lot more questions for you to work through. I'm getting really tired, so I will not verbally go over all these questions. I try to put in my working as detailed as possible. Hopefully that's enough for you to understand. I do want to address this question. Astronaut is at rest and he's this heavy. He fires a thruster that expels 35 grams of gas at this certain speed. And so this question is an interesting one. The gas is going this way, and the astronaut, I think he's going to go that way because action-reaction. So after collision, you treat this as an event, all right? Event means collision in physics, or other events. Explosion can also be an event. But after the event, you have two masses traveling in opposite directions. So we would treat this as a elastic collision. So you're going to use that m1v1 m2v2 equals to m1v1 after collision plus m2v2 after collision. All right, so I'm subbing in all the numbers. Now, if you think about it, the astronaut and the thing that he fires were actually at rest together because he was holding onto it. So both of these have zero velocity. That means you don't even have to do any calculation on this side. Everything together after calculation would be zero. On the other hand, though, after the event happening, the explosion happening, the gas is moving in this direction at a certain speed. So that's my object 2. This is my mass 2, velocity 2 after the event. This is my mass 1, and what we're trying to find is the velocity of the astronaut after firing the thruster. So that's the reason why I've subbed in these values the way I did. And calculate it, and you should find this. Don't forget that you need to make sure you have the correct positive and negative, because this is a positive value. After moving it to the other side, it needs to be a negative. So you need to change it. Okay. Yeah, I'll let you read the rest of them. The last question that is in this practice set involves a two-dimensional momentum question. What we've been doing so far is only one directional, so that means it's either positive or a negative. This time, what you have is an object traveling this way being collided by an object traveling this way. And what you'll have after the collision is this, because you're actually combining the direction of these two objects. And if you were to calculate this, you have to calculate the momentum on the x-axis and the momentum on the y-axis separately using sine, cosine, and that kind of stuff. And so I'm not going to address this in here. If you want, you can go and ask your physics tutor, or you can just do it on your own if you're very advanced in mathematics. But I won't waste my time.